and that will be posted to our YouTube channel, so you can access that at your leisure. For those that have questions, if it's not of immediate concern, if you don't mind, please wait till the Q&A session towards the end of the session, and I'd be happy to answer questions for you related to the content here that we're going to go through today. So we're going to start. In the last few webinars, we've looked at and we've talked about different ways of creating a model. So I'm not going to go into great depth on that. I just want to make sure there's that people know about I would say the primary ways of generating a model. If you've been involved in any of the previous seminars, we've shown the CAD conversion. I'm not going to go into that in any detail today, but a couple of other ways that you can create an adapt model would be through Revit import and also through what we call the adapt integration console with Etabs. I'm going to start with that process. And here we have an Etabs model. This is limited to static lateral loads and gravity loads from Etabs, just as a qualifier here. But we have a multi-story Etabs model, and let's assume that we want to do some preliminary column sizing or even foundation sizing for the columns or maybe the shear walls in this building. But we want to do this maybe in Adapt. And so we have this model set up in Etabs. There's three things that we can import to Adapt. We can import the geometry, we can import applied loads that are in the Etabs model, and if the Etabs model is solved, we can also import from Etabs to Builder the reactions. That's more of a special case where you might want to combine the reactions of a lateral analysis in Etabs with gravity results or gravity loads, including post-tensioning inside of Builder. So we're mainly going to use this to extract the applied loads and also the geometry from Etabs. So I've solved this particular model in Etabs. I'm going to also export an XML file for the story forces. So I'll go into Etabs and under the analysis results, structure results, story forces, I want to create this XML file. And I'll go ahead and just save that into this default folder for this particular webinar. This is just saved as an XML, and it will contain the story force data that's needed for our integration console to extract and be able to write it into Builder. So once that's done, I'll close Etabs. We do need an active license of Etabs available for this to work and function properly. So the Adapt Integration Console, the latest is version 7. I'm going to use this console to extract the data from Etabs using their API, write an IMP file for Adapt, and then import that file into Builder. So this is a go-between of both programs. So I'll use the Etabs 17 option. And by the way, this is a free program. If any of you would like this, just let me know afterwards. You can send me an email or give me a call, and I'd be happy to send this over to you. I'm going to browse to that file. Okay, I'll load the model. I think okay, it says it cannot start Etabs. So let me see if I have Etabs open. Give me one moment here. Okay, that is not open. Let me just try this. Version 16. All right, so obviously we're having some technical difficulties here. So ultimately, using this tool, which I know some of you that have joined the conference have actually used this. You can vouch for me if I could bring you online. But anyway, using this tool, we would ultimately end up with an IMP file that is imported into Etabs. And if you'll hold on just one moment, I'm actually gonna grab an IMP file, and I'm going to show what that looks like. So I'm just using a different machine here to access the file. If you can bear with me for one moment, and then we can take a look at that. Okay, so for the same model, I'm just going to abandon that. For this same model, I've created an IMP file previously, and I'll go ahead and grab this file. This is just the generic format IMP that we use not only for Etabs but also for Revit, for any integration that we do with other third-party programs. So ultimately, this is the outcome of the integration console. I apologize for the technical troubles there, but I'll open Builder, and in Builder, we're going to import that file. Now, you want to make sure that when you launch Builder, we understand what the different selection options are. So as part of this webinar, we want to introduce what are other components of Builder that can be used in conjunction with just the single level Floor Pro module. So I'll define these before I actually import that. The programs we're going to mainly look at Edge today and Floor Pro. Mat and Floor Pro, these two programs are very similar in nature. This is to design elevated floors. This is really used to design foundations, mat slabs, footings, pile caps, and so on. The forces and the actions that we design for stem from our general frame solution. So the frame solution can be a single level solution, or it can be a multi-level solution. If we want to analyze a multi-level model, then we have to have Edge open. And so Edge and Floor Pro can be opened in tandem. Edge and Mat can also be opened in tandem. Floor Pro can be opened individually, as can Mat, but this means that the analysis is limited to single level, not multi-level. So in this example, we're importing a multi-level model in. We're going to be using that really as the basis for the webinar. So we're going to select Edge, Floor Pro. We don't really want to focus today necessarily on post-tensioning. I'll go ahead and just limit this to RC. And modules, we're not going to export any design strips to our 2D program, PTRC. I'll leave that turned off. PT Shop module, I'll leave that turned off. That's mainly used for shop drawing production, elongation calculations, and output, and long-term, short-term losses, and so on. So we'll go ahead and just, again, Edge and Floor Pro are the two primary focuses at this point. We'll go ahead and select OK. And now I'm going to import that model from the integration console. So we'll select the IMP to import. That will be this 25-story IC test IMP. In the import options, we're going to import the entire model. You'll notice that when we create the new model, everything is selected. That's good. We'll say we're going to import everything. Under load cases and loads here in this second tab, now we have the ability to kind of filter what applied loads and what reactions we want to import. In our case, we don't want to import reactions. I'm not going to utilize the Etabs reactions for any purpose for today's webinar. We really just want the input, meaning the geometry and applied load. So for the load case dead, this is a dead load. I want to import applied force only. Notice you could also import reactions only, or applied force and reactions. There's multiple selections here based on what's present in the Etabs solution. So we're going to do applied forces only. Live load will do the same. Wind X, I'll write in the wind X forces that were specified in Etabs. I'll write the same ones into Adapt. Wind Y. Self-weight, I want to auto-calculate that inside of Adapt. I don't want to bring in the self-weight from Etabs as an applied load because, in my opinion, it becomes a little troublesome to track and trace those loads. Once you import it in from Etabs, it becomes a dead load, not a self-weight load. So self-weight in Etabs or in Adapt is strictly limited to the actual self-weight that we calculate native to our modeling environment. So here I'll select none. EQX, I'll say this is seismic, and this is going to be applied only. EQY, same thing. Okay, and then if we want to map any of the loads to existing load cases in Builder, we can map to existing. So the only two that I'm actually going to map are dead and live. In Etabs, it's called dead. Live load is called live. In Adapt, the default is called dead load and the default is called live load. So we're going to map the names to the names that are already designated inside of Builder, and we'll set that up here under the map to existing. Okay, under load combinations, we could import the load combos from Etabs. I'll choose not to do that in this example, and then I'll go ahead and import the file. Now we need to set this to wind. So this is a fairly big model. It takes just a moment to import this. All right, we have our model in our Builder environment here. So notice if I was to open that Etabs model back up, this is the same model that was imported from Etabs. So there were no smoke and mirrors in me trying to get this in from Etabs, other than the integration console was misbehaving there. In this example, you can see that if we look at this model, there are 25 floors. A couple of things to note. The lateral loads, wind X and Y, EQ X and Y, when we import those from Etabs to Builder, they're imported as what we call generic lateral loads. So under the loading menu, under the lateral load wizard, you'll notice that these have actually been imported as lateral load or generic lateral loads. There's wind X, wind Y, EQX, and EQY. And you can see for the different load cases, the program essentially defines a story force associated from Etabs into Builder. And we can then basically treat these as loads that stem from inside of Builder. Okay, how is this solved? There's different classifications for lateral loads in Builder when we want to analyze a multi-story frame. There's a wind load, which is an applied external load. You can see the wind load wizard. If I use the wind load wizard to generate load cases for wind, all of the loads are externally applied line loads. So they're not really subject to discretization to nodes in the model. And there's a question. Let me go ahead and answer this. The question is there any way to see in the Adapt model where those generic lateral loads are applied? Yeah, Marcus, I'm getting to that. I'll explain that here in just a moment. There is a place where we can see that. So the types of lateral loads, wind load, if I take this model and I apply wind load, and I'm not actually going to do it in this model. The model is too large to run, in a limited amount of time, but this would apply generic line loads. Seismic load wizard, applies story forces that are then distributed to nodes. So these shells, this diaphragm is essentially a semi-rigid diaphragm. We apply the total story force from seismic or from lateral load wizard as a set of internalized nodal loads that we distribute at each node. Okay, and there's a way to see where or what portion of the total force is applied to which node. It's a text file, so it's not as easy to maneuver, but we're going to give you an example of seismic load wizard and also lateral load wizard. But the first thing we wanted to show is what's one way to construct a model that's already in place. One way is through the Etabs integration console, and that's what we've shown here. Another option is to construct a model through Revit Link. We've showed this a few times in previous sessions, so this is nothing new, I think, to many of you. If we use the Adapt Revit Link, we can go ahead and export this model. This does not have any loading in it, and we'll export this model out of Revit. I'll generate again an IMP file for the geometry in this example, and let me go ahead and save this. Okay, this is not the same model, by the way. This is a smaller model that we'll likely use for the remainder. So if we take this model, and I'll go back and open Builder with the same settings, Edge, RC Floor Pro. I'll import the IMP file for this Revit model. It's the same format, the same dialog. The only difference here is there's no load cases that were defined in Revit, so I don't really have any selections to be made in load cases and load combos. We're going to set those up inside of Builder. Okay, so I import this model, and again, in this case, I really just have geometry. But now we want to define, okay, downstream, we're going to look at column design and wall design. So we want to define some of the lateral load options within Builder. How do we define these? First thing we'll do is define just some very basic gravity loads. So let me save this model. And I'm going to just select by type all of my slab regions, and I'll add some basic uniform loads to my slabs. The dead load, this is superimposed dead, I'll say is 20 PSF. The live load, we're going to say is 50 PSF. Okay, and I'm also going to go ahead and add first wind load. So we'll go to wind load, and I apologize if these inputs are not identical to what they should be for this type of a structure in terms of its wind speed and different parameters and factors. But we'll first define the direction of the load. So this direction, we're going to say the primary wind direction is 0 degrees. That means it corresponds to the global x-axis. This is positive, and this is 0. This is positive, and this is 90. So if I input 0 and then orthogonal direction, we basically get a set of loads in the positive global x and the positive global y directions that the program will generate based on the edges of slabs that are defined in the model. You can see that there's two load cases automatically defined. There's wind load, or wind P0, which is really the x direction, positive x, wind P90 is positive y. If I wanted to apply loads in the negative direction, then I could use, let's see, we could use 180 and 270, and that would be the negative x and the negative y direction. Okay, so you can define as many repetitive loads as you want with different degrees of application in this dialog. So I'll use orthogonal direction. I'm also going to include torsional, just the eccentricity of 15%. And by doing this, I introduce two additional load cases, wind M0 and wind M90. Okay, and this is 15% eccentricity would be if we have a slab that looks, like this. This is our X direction. We take 15% of this edge and we, generate this moment, and then the same thing is done for this face here. We generate that torsion based on the distance or the edge of this slab and the eccentricity percentage applied to that. The program cannot actually apply a rotational drilling moment around the z-axis. So in order to simulate this, we actually produce a couple. We produce a line load in one direction. So this is, if we take a resultant, this is our, let's say, X positive, and this is our X negative. And that produces a rotational moment for the slab and for the entire system. Okay, so let's go ahead and add some numbers here. We'll say the basic speed is 120. I'll leave the coefficients as is. This is really geared towards an enclosed structure. So the internal coefficients we'll assume cancel, and we don't have those in terms of the input. We have the leeward and windward coefficients, gust, topographic, and directionality factors. Once we generate all of the input data, then the program will essentially produce a force, a windward force and a leeward force. In the case, for example, of wind P0, the windward force is applied on this side, the leeward force is applied on the back side, kind of pulling on the structure. If we wanted to reverse direction, the most 100% accurate way would be, again, to generate another load combination set with 270 and 180 as the input angles. But because this is a solid, let's say, diaphragm, a lot of times users will simply do a plus minus in the load combinations. Okay, the plus minus does not transpose the two forces. The plus minus simply flips them. So you're still actually applying a windward force in the opposite direction on what really is the leeward side technically. Okay, so there's a couple of ways to handle it. This ultimately, if you have a solid diaphragm and you don't have components that are transferring load into the diaphragm, then this works pretty well using the plus minus. Ultimately, the load's delivered into the diaphragm, but the most accurate would again be to use different angles. The question is, what is this drawing tool that I'm using? This is not an Adapt product, but they should allow us to distribute it because people ask that quite often. This is just a tool that's free online. I think it's called Epic Pen, but we use it internally to mark things up. Maybe we should do an add-on inside of Builder for Epic Pen. So, all right. So what we have is we have 4 load cases that are going to be applied to the structure. And this, if I let that run, this will basically generate all of my applied lateral loads to this building in terms of wind. Notice that these are basically just line loads. If I go to any level, I'll just switch this to single level 15. And I double click on one of these loads. That load is editable. I can take any line load now and edit it. I can delete it. I can change the force. And I can add additional loads to it. There's multiple things I can do with that load. It's as if I just simply added it manually to the model. So it's all done in terms of Wind Load Wizard as external applied line loads. Now my model is not responding here. Let's see what's going on. Still catching up. All right, I'm gonna close and reopen for sake of time. Oops, let's see. Looks like it might have come online there right after I had done that. So Back to that model. I'll come back over to loading, Wind Wizard. I think it dumped that because I hadn't saved it, and I'll just do the same input again here to generate those loads again. Okay, I'll turn the loads off for just a sec. I'm also going to add back in the gravity loads. I think those were not saved also. Live load, I think we said was 50 PSF. Okay, and I'll save it this time. Note that the building loads, wind, P0, P90, M0, M90, those are stored as building loads. That means they're only solved for when you run the model globally or in multi-level mode. If I try to solve for wind P0, which is a set of loads that applies to multiple stories, and I try to model this or analyze it in single level mode, it won't solve that load case because I need to run it globally in global mode. Okay, so those are the wind loads. Now the seismic and lateral loads, those behave very similarly. If I go to seismic load wizard, and I'll just call this EQX, and the load generation tool we're using is ASC 710 with some different parameters for generation of the base shear. You could also, by the way, use user define, and you could user define the base shear, user define story forces, etc. So there's different ways to generate the loads at each level, but ultimately we need to come up with a story shear at every level in the model. So I'll define this as EQX. I'll apply that. Notice when I apply that, nothing really happens. When we applied the wind load, the program sequentially went and added a bunch of line loads. When I apply the seismic, it basically stores the information that we've written into this window. Okay, and I'll change the direction to 90 degrees for wind or EQXY, EQY. And what's happening is the program will take this information and it will determine the story force unless I define the story forces manually, which I could do. And using this equation for seismic mass, which is 1 times the self-weight, you could edit this. I could include a portion of the dead load, the live load, any other loads that are defined. We could introduce into these combinations, which is used to define the mass. Once we set up this data, let's assume that at level 15 again, I'll use this as my example. Let's say that based on that data, the shear in this level is 100 kips. And rather than us assuming a rigid diaphragm and saying, okay, the center of mass is right here, and we calculate the center of rigidity, and then we apply this, in that fashion, because our diaphragms are not assumed to be rigid or flexible, they're just, in essence, they're semi-rigid. They're a shell element. They have both in-plane stiffness and out-of-plane stiffness. We basically take this total force, and for every node that's generated and connected to this level, we take the total force, I'll call this F, and we take the mass of a single node divided by the sum of the mass connected times the force, and we apply that force to each node. So every node gets a portion of this total force. If there's eccentricity and you also have moment, every node gets a portion of this moment as well. And in order for this to be solved at the onset, when we say, okay, mesh the structure and now analyze it, when you press analyze, the program, as part of a pre-processing input, will label the nodes. It will say, okay, here's node 1 through node 1000. And once we know the labels of the nodes, then we can assign the forces and the moments for seismic EQX or EQY to those nodes. And that's why you don't really see anything happen, because it happens at the onset of analysis. the exact same thing is done for lateral load wizard. Okay, this is really just a way to generalize a load case that's lateral, and for the user to just simply define the story force. So in one case, we're having the program ASC 7 calculate the story forces, and then we'll take those and distribute them based on what I had just described. In the other case, I could say this is also going to be EQX lateral, I'll say lateral load wizard. But here I would have to write in the story force. This is just a manual operation. Okay, and when we import from Etabs, it actually gets written into this context versus into this wizard, because our wizard is what solves the force. The forces have already been solved for in Etabs. We already know what they are, so we import those directly into the lateral load wizard, which ultimately gets processed identical to seismic loads from our seismic load wizard. Okay, so these two are identical in the way they're treated. This is an external applied load. This is an internally applied load at the level of nodes in the model. Now, if we let's go ahead and solve this, because I want to answer a question that was brought up. In order to solve lateral load cases, we have to use finite elements in our program. If we want to only solve gravity load cases, we can use tributary, load takedown, or we can use finite elements, one or the other, or envelope the both, right? So what we're going to do is we're actually going to solve this model for lateral loads, and we'll use FEM to do that, but then we'll use load takedown to solve for the axial loads in the members, walls, and columns, and then we'll combine the two for purposes of design of columns and or walls. Notice in load cases, we added two new load cases, EQX and EQY. Okay, so under load combos, we have some default combinations. And this kind of creates a disconnect with a lot of users, actually, but I wanted to kind of show what's going on here. So these are just default combinations that are generated gravity only by the program. And rather than go into a long description of why we don't generate the combinations automatically for lateral, I'm going to show you how you can input those. So ultimately, at this point in time, this is Builder 2018.3, a user would need to actually combine and generate the combinations manually in this interface to include wind, gravity, and seismic. Okay, and that takes time. I mean, you could have 300 combinations you have to enter. Once they're entered once, then you can save them, and you can save it as a template, or you can just re-import an IMP file with load combos and be done with it. So I'm going to actually do the second option. I'm going to import an IMP file that already has all of my combined combinations with gravity and lateral. So I'll go ahead and select this. I'll select this if I can find it. So actually, it should be under, let's see, code combo input files. Okay, so we're going to use master loading ACI as this IMP file, and if any of you want this file, let me know. I'll be happy to send it to you. When I import this file, I want to update. I don't want to create a new model. If I create a new model, it's going to override what I've already done. So I'll update this. I'll deselect any component. I don't want to import components. I just want to import combinations. I do not want to import any load cases, but I do want to import this entire list of combos. This has ULS and SLS combos for lateral, wind, and seismic. Okay, I'll import all. And in so doing, the program imports, I think there's 250 combos or so, somewhere around that number. So this takes a little while to populate that list. There's 240 combos. Okay, so those have been now included in this model that we're using. So now I can actually generate a solution for different combinations, including all of the different permutations of wind that you must analyze, you know, in terms of ASCE 7, where you have torsional effects, and you have basically 4 different cases that get extrapolated into probably 24 or 32 different permutations of those cases. And that's what these first set of combos are. Those are just the individual wind cases. And then we get into the ultimate limit state and service limit state combos that include gravity and wind. Okay, and these are all based on ACI, and we'll go ahead and also ASCE 7. So we'll go ahead and close that. Now I'm not going to run all the combinations today, otherwise we'll just be sitting here watching the thing process, but I want to give you an example of how this can be processed for the purpose, again, of designing columns and walls. Right now, by default, all of my columns are fixed to the slab, meaning I have not released rotation. If we assume that this is a shear wall building and maybe I do not want my columns to participate in the lateral system, then I have to do something with my columns. So I'll select all of my columns, and I'm just going to pin all of the columns. I'll say they're linear columns, and I'll go to into multi-level mode. If I'm in single level mode and I select my columns, it's only going to select those that are shown here. So I want to go back to multi-level mode, and I'll select by type. We're going to select column. Okay, and for this particular run, I want to pin my columns. So I'll go to modify the selection, and for this selection we'll say column, and I'm going to pin for rotation top and bottom. I'll just make sure this is checked. Okay, checked means you're releasing. This is top and bottom. Check box means you're releasing the, if it's unchecked, you're not releasing. If you check it, you're releasing. So we'll check those for columns. I'm also going to generate a stiffness usage case. So I'm going to assume that the slab is cracked, and I want to assume that the wall is cracked for my run. Let's assume we're designing the columns in this case at ultimate limit state. So the default usage case is actually called uncracked. If I double click on any component, you can see this says this is uncracked. Everything is set to 1. All right, so we're going to set up a new usage case also, and I'll go back and say edit usage. I'll call this ULS columns lateral. Okay, and I want to now select the components that I want to apply modifiers to. So I'll select first my slabs. I'll just window select my slabs. I'll modify the selection again. Since I'm modifying more than one component, I always need to use this modify selection. And for my slab region, I'm going to go in here and change the bending stiffness to 0.25. Okay, I'll select again my, let's say my walls. And I can set those. I'll use points. I don't know if these are exactly correct based on what's stipulated in the code, but we'll just set these all to 0.7, even for the axial and shear. Okay, and we could do the same thing for columns. I'm going to leave the column set to 1, again, just for sake of time. You could set up as many usage cases as you want. Okay, when you run the analysis, you tell the program, use this usage case. I want to use this stiffness profile for this particular analysis run. All right, so my next thing that I'll do is I'll mesh this. I have to mesh and run the finite element engine to solve this if I have lateral loads. So I'll set this to something rather high just so we can solve this fairly quickly. Okay, so we're going to execute the analysis for this frame, and you're going to notice when I run a model globally, there's everything over here is actually grayed out. None of this actually applies. This only applies when after we've obtained a tributary or global multi-story solution, we can actually extract reactions from either of those and reapply them to a single level floor or foundation. Okay, so this is inactive because we're solving everything anyway at once. For this example, I'll just run maybe 3 or 4 combinations, and you'll see here where it says apply stiffness, I'm not going to use uncracked, I'm going to use ULS columns lateral. And then I'll come in here to this list and I'll select which combos I want to process. So we'll do this one, that one, this one, and this one. I have no idea which ones those are, but they're all wind combos combined with gravity. Let me choose one seismic, and there. Oops. Try that again. We'll do 2 seismic and 2 wind. Okay, so these are the combinations that we're going to design the columns for. Now, in this case, you know, the columns might be designed only for gravity load combinations since they're not really participating laterally, but we'll design them here anyway. We'll also design the walls for these combos. So we're going to run this analysis with this usage case to get a solution. So once we have this solution in place, we have basically a global FEM solution. So while this is running, it says there's boundaries of patch loads overlapping on itself. Let's see if I can quickly identify what's happening here. Let me go into loading. Okay, I'm going to turn off. I'll go to patch load, dead and live. Oh, okay. And I'm going to select. Oops. I'll select patch loads and line loads. And let me try this again. So slab region. I'll go right back to analysis and see if this runs. Okay, this thing. All right, so what we're going to do is eliminate the loads, and we're going to run it for self weight plus the lateral. It's hopefully this runs. Patch load 1. I think we have any more patch loads in the model. Let me try one more time to see if there's anything else. It thinks there are other patch loads in the model, but I don't actually see them. Let's see if I can select patch load. Okay, I'm going to save this now and reopen this. Okay. All right, I'll give this one more try before I abandon this model and try a different model. So let me select the slabs again. Let's say 0.05. We had a couple of wind cases, and I'll come down here and do a couple of the seismic. Okay, it looks like it's going to run. So while this is running, we have, if we think of this as kind of containerized result, our ultimate goal in this case might be to design walls and columns, for example. And so we have, column design, wall design. The question is, where do the forces come to design these walls and columns? And down here, off to the side, there's a couple of boxes of solution. So over here we have an FEM solution that we'll call this FEM. And this FEM solution stores whatever the last saved run was. So in this case, we're running, oops, let me just close that. In this case, we're running self-weight, gravity dead, gravity live. We're running wind X, maybe wind Y. I'm not sure which ones were selected, EQX and EQY. And we have solutions for all of those load cases. So those are the finite element results for this global run. Okay, if I run it a second time and I run it with uncracked, this basically gets overwritten in terms of its availability for just direct FEM results that you can navigate within our interface. In terms of design of walls and columns, if I run FEM once, I'll call this FEM1, and that's the usage case that we selected for column design lateral, and I run FEM twice, but this is now the usage case. I'll call this FEM2. This is uncracked usage case. This is cracked usage case, essentially. These both get stored. I can access reactions from both solutions. So I don't have to run multiple models, save one as uncracked, save the other one as cracked, save the other one as cracked even more, and so on. All of this data is stored here. There's also this bucket where we have a tributary solution for gravity loads only. Okay, and we haven't run that yet, but there's another potential silo that stores that information that can then be called on when we design the components. So here we've saved FEM1. That's the cracked run that we've just processed. Okay, now what we're going to do is we're going to process the tributary loads. And it doesn't have to be in this sequence. I could do tributary loads first. I could do FEM first. I have to run FEM because I have lateral load cases as building load cases. Let me go ahead and go back to my default display. So now I'm actually going to run the tributary solution. So I have the possibility of enveloping the vertical reactions in the columns or walls, let's say the axial load between the FEM solution and the tributary. So I'll go to loading, load takedown. This has really nothing to do with finite elements. In fact, I don't even have to mesh the model to do this. I'm doing this after the fact, but this could have been done first after we had imported the model and loaded it. Here I'm going to regenerate my tributaries and I'll calculate my loads. Okay, so the program has essentially created a tributary zone for every vertical component. Let me go up to level 15 here. I'll use my results browser to look at this briefly. So we'll go to the load takedown, tributary boundaries. These are basically the tributary regions for each vertical component. For example, this column here. If I look at the cumulative loads in that column, and I just go down to the first elevated floor, let's say plane 2, these are the load accumulations based on geometric tributary. So you can see the dead, live, and self-weight. If I turn on the FEM global solution, for example, here, this, I don't know why it's not showing the dead and live. I'll have to check that. But notice that the tributary solution is 863 kips. The FEM solution is 944. FEM is based on the stiffness, the relative stiffness of the components. So this result is not going to be identical. One of them is, ignores stiffness, is based purely on the geometric region that we define. The other one is 100% based on stiffness. So there's a difference here between the two. What I wanted the primary reason I'm showing you this is you have two alternatives for generating the gravity axial loads for the columns, and you have the possibility of selecting either one or enveloping them when we design a component like a column. So right now we have those two buckets, those silos with data. We have a FEM solution and we have a tributary. Now it's time to design a column or a set of columns that can tap into those two buckets, if you will. So I'll go to the multi-story mode again. I'll just turn off this stuff here. Okay, and I'm going to design this stack of columns right here. You'll notice if I double click on this column, it's a 22 by 22 square. Right now there is no section type assigned. So in order to design a component, a column, we have to define a section. Okay, there's a question. Sorry, Sungyab, I did not see that. I assume that your 1.4 dead of the seismic came from this 1.2 plus 0.2 SDS. Correct. Yeah, this is obviously site specific for this this parameter SDS. So yeah, my combinations are based on a specific SDS and SD1 parameter. You will have to modify your combinations for those combos that include a portion of the seismic dead load, the component of the seismic that contributes to that combination. That's a good question. Yeah, I should have mentioned that in my combos. So the question really is, when I look at my load combinations, and I go down to the seismic combos, you can see some of these combinations are predicated on having a portion of the seismic effect, be included as part of that dead load of combination, and that's specific to not just some hard-coded factor. It's specific to the actual values that are for a given site. So make sure you adjust those accordingly. Okay. All right, so back to the column design process. If we take these columns, we're going to say that we're going to group these columns as a specific design group. That means I want to design them as the same size and the same reinforcement. And we'll go ahead and I'll select those columns. I'm going to assign them to a group. Ultimately, if you want to design columns in the program, they all need to be assigned to a group for those that you want to design. So I'll go to column. I've selected these columns here, so I'm going to modify them and I'm going to assign these to a new group. Okay, and we'll assign those to a group. The group name that the program assigns is just the size of the column. Okay, it's been actually rounded, or it's the precise 21.99 by 21.99. That information is stored in a type manager, a section manager. So if I go into the section manager for column design, I'm going to first say this is 22 by 22 grid Spencer. Okay, whatever you want to describe it as, name the column group as that. And now we have to define, let's say, the beginning reinforcement for that column. So here I can define, a set of bars, both vertical and also the column ties for this particular group. We're going to say the bar size is 9s. I'm going to use 3 and 3. My row is 1.65%. And then for my tie size, I'll say it's a 4, and the spacing is 8. So you'll want to familiarize yourself with these different parameters, and this just defines a starting point for the column group that we want to check. So we'll say, okay, that's fine. Now, if I double click on any of those columns in that group, you can see the section type is listed, and I can edit directly from that dialog. Okay. Under design settings, now we have our combinations list. Notice the only combos selected are those that have a result for them, right? So technically I could select any combinations in this list because every one of those combinations already contains a load case, or let's say a partial set of load cases that have been defined or have been solved for. So the combinations that I selected, there were 4 of them. I solved for self-weight, I solved for dead load, live load, and then I solved for wind something and earthquake something. So there's already solutions for all of my gravity loads. So if I wanted to design the column for service total, which is self-weight, dead, and live, I could actually do that, and the program recompiles the forces for this one combination when we pass it to the column designer. But by default, you'll notice if I scroll in this list, it only selects those that I actually analyzed up front. A few important things. For source, if I use tributary method, I'm only accessing the tributary axial loads. In this case, I would be only designing for axial only. If I use FEM, the program actually filters this list. It only shows me the combinations that I have a solution for in terms of FEM. Okay, if I go to envelope of FEM and tributary, this actually allows me to envelope the axial from FEM and tributary. Okay, you'll notice in that in the view that I showed earlier, the size self-weight was different. Here we would envelope and take the maximum of those two to design. And then finally, you could use the FEM moments and the larger of the tributary FEM axial. So this is a combination of those two buckets. For the moments, we're using that left-hand bucket, which was FEM, and for the axial, we're actually using the maximum of both of the buckets. Okay, so this is different options you can use for setting up the column design. The FEM source, we want to use global analysis. That's the analysis we just ran. We can also choose to reduce the live load if we've set up live load reduction for the columns. And then there's some other options here for column design. Ultimately, after you set up your column design settings, I can now code check this group of columns. So I'm code checking an entire group, or I can code check one of the columns in the group. If I, for example, say I want to just code check this lower column, I can select it, right click, column design, code check. And that code checks one column out of a group of 5 columns that are assigned to this group. The program will code check. Once it's code checked, now I can access a summary for that particular column, a design of that, or a summary of that design. Really, it's not a design, it's a code check. You can also graphically, I'll code check all of them now. We could graphically produce a result for the code check of the columns as well. So once I code check all columns, and graphically I want to see the result of the code check for that entire string of columns that belong to one group. And that makes it a little easier to isolate and identify columns that may or may not pass based on the reinforcement that we assigned to the column. Okay, so once that's done, if we go up to column and we go to individual column design result, I'm going to look at the status. You can see everything here passes. That's not really descriptive in terms of what's passing or what's not passing. If I go, let's say, to axial versus moment interaction, again, this gives me some utilization, 0.06, 0.13, 0.19, 0.26. So this is really just binary. It's either acceptable, unacceptable. If you wanted to make this a little more descriptive visually, we can always change the display under the components. We're going to change the utilization to not status but a value, and now I get a range of values along that actual string of columns for the code check. The red doesn't mean it's not passed, it just, this is the highest utilization for that bending axial interaction. Okay. There's a question here. What is the difference of the design within Adapt and S-Concrete design within it? Marcus, the question is there, or what is the difference between Adapt designing the columns and S-Concrete? Adapt column design uses S-Concrete 100% of the time as the back-end design engine. So in order to design these columns, I have to have a license of S-Concrete, but notice I did not have to actually go into that program. Everything is done. We write all the data on the back end into a formatted file that can be interpreted by S-Concrete. It's all processed on that back end, and then it's pushed back into Builder so we can see the results in Builder. So when you do column design in Adapt Builder, it's always done by S-Concrete. For example, if I take this same column and I open it in S-Concrete, now I can actually open that program to see the results within that environment, but it's not required by Adapt. We can do everything inside of our own interface. But we did not write the engine that actually designs the columns for column design in Builder. So this is actually S-Concrete that I've opened up that one section inside of. You can see the same utilization, 0.32 is shown. I could modify this. Maybe I want to change it in S-Concrete to 12 number 9s, and that will update the results. Maybe I back it down to 6 number 9s or 4 number 9s. Again, you could make changes here. Whenever you come into S-Concrete and you make a change, it stays there. It doesn't propagate back to Builder. So that is just a brief example of column design in the program. Now the time, we've gone past time today, so what I'm going to do there, I'm actually going to stop here for today. I know we published 1 hour, so we want to try to keep with that in good faith. And what I will do is I'll actually set up a second continuation of today's meeting to get through some of the other aspects of Builder, wall design, and and also foundations, how we can utilize a multi-story solution for looking at foundations with the reapplication of reactions, because that's important to understand in context everything that's involved in Builder. I will make sure to send the invitation to those who actually who had signed up for this meeting, so you have first opportunity to join that second meeting, and we'll do a continuation session. Okay, so I appreciate everyone's time today. There is a question here. Can you get PDH certificates for the webinar? Yes. If you contact us, we will issue a PDH certificate. You can send the request to support@adaptsoft.com, and we would be happy to send out PDH certificates for those that contact us. Again, if you want any of the sample combination files, I'd be happy to send those also to anyone interested. So again, thank you. I'll reserve the next 5 or 10 minutes here for questions if you guys have any questions to ask. And you can unmute, or you can just chat in the chat box. You can type in the question. Okay, doesn't look like there are any questions. Let me just see here. There is a question. Question is, does S Concrete calculate K values for columns in sway frames, or it always assumes 1? S Concrete does not calculate sway columns, so that puts us in a bit of a bind, because in Adapt we can model a frame that has significant sway, but in terms of passing the moments to S Concrete, they don't actually magnify per the sway method, let's say from ACI. So the current implementation is really geared towards non-sway columns. Now, with that said, in our next release of the program, we have included P delta effects and second order analysis. So, you know, if you use that option in the next release of the program, then technically you wouldn't have to use the magnification method to begin with. That's our solution for that. But yeah, S Concrete does not design for sway columns. In other words, K is always equal to 1. Can we export the calculation to S Concrete to design the reinforcement? Yeah, Miriam, the program works in dual mode. So you can actually do a column check, or you can design a column. In my case, I was just designing or code checking. But if I wanted to design a column rather than code check, I could always select to design the group. And when I design the group, the program will actually design the reinforcement. It will propose a design if the current column does not meet the requirements. So you can see here the current value is all kind of set. The utilization is 0 because this is the first pass. The current number of bars is 8. The proposed value is 8. Why are they identical? Because the current value already satisfies the code check. But let's assume that the moment and axial utilization was 2. The program would actually design and propose a different number of bars for you to meet the requirements for the design. So there's 2 modes you can work in. You can work in code check, or you can work in design mode. Other questions? Uh, the check, it considers the reinforcement. I mean, it has to, the reinforcement is considered in terms of strain compatibility for the code check. The program will produce a interaction based on what rebar is there, and that means that the program must consider the reinforcement in the section. Okay, any other questions? All right, I will make sure to post this to YouTube, and then we'll set up a continuation session that will send out invitations for all of you for, and we'll continue on with this session today. Thanks again. Have a good day.